and today we are going to study logistic regression. What is logistic regression? It is a process of modeling the probabilities of a specific outcome. You are modeling probabilities of specific outcomes for given input variables. They are generally used in situations where we have a binomial distribution of our data where the values can be either 1, 0. They could be categorical, such as true, false, such as healthy, unhealthy. So these are some of the categorical distributions where we can use our logistic regression. And when we have not just two classes, when we have multiple classes of our data, then we can use multinomial logistic regression. When we have more than two possible outcomes. So these are the application reference where we use our logistic regression. When we have distribution in categories such as 1, 0, true, false, or we could have multiple classes which are more than one. For example, digits 0, 1, 2, up to 9. Here we have 10 classes. Here also we can use multinomial logistic regression. So in the linear classifier, what we were trying to do was to find a boundary between our classes such that the value at f of x linear regression line was, here at this point it is 0, and if you go below this boundary you get, for example, a 0 or -1, and if you go above this boundary you can get the function value to be +1. So this is your linear classifier concept that we have studied before, and here we can see that we can determine a hard boundary, either 0 or 1. This is known as a hard boundary, where the actual value of all these points should be 1 when they are above this line or this function value. And if they are below this function value, then we say the blue dots, they are 0. So we need to define a classifier which decides this, how we are going to classify our data. So what is the target of linear classifier? It finds a linear boundary which is best discriminating the two classes. So we have to find the linear boundary in the linear classifier. And as we have studied in linear regression, that can be done the best with minimizing the error. And error is the number of misclassified instances. So either they should be 1 or 0, but our classifier or function classifies that the dot was red, but it predicted or classified as a 0. So this actual versus the predicted, they are differing, so the value will be misclassified. But if the value is 1 and our algorithm predicts 1, then we say it is correctly classified. So we need a classifier h of x which minimizes, as we all know, the absolute error and the squared error. The difference here between the previous lecture that we studied about linear regression or multiple linear regression, here h of x can belong to either 0 or 1. Also, or yi can be either 0 or 1. So when we have a value of either 0, 1 or either 0, 1, in that case, we are going to use our logistic regression. Here, there's a new form of a function you could see here. H of x, function which takes two values, h of x, a function, a classifier, and y of I, where this I, a and b, it can take up the values of 1 or 0. When a is not equal to b, we say it is 1, and when a is equal to b, we say it is 0. What does that mean? When h of x of I is equal to yi, what does that mean? That it is correctly classified. This is our predicted, this is our actual. It is correct classification. However, if hx of I is not equal to y of I, we say it is misclassified. And the more misclassified instances we have, the larger will be the error. So error is the number of misclassified instances for our classifier h of x. We are trying to minimize the error. Misclassification error. For a given data with n data samples, we have pair di, which is xi, yi, and xi variable can take the values up from 1 to up to xt. And your yi can only take the value 0 or 1. So we have to find w, the regression coefficient, which minimizes the squared error. And we can write it that our classifier h of xi should be 1 if our function f of x is value greater than or equal to 0, where we can define f of x as we did before, w0, w1, x1, w2, x2, wd, xt, or starting from x0, where x0 is 1, we can also write it as j of 0, where xi, j, and wj. So this is the same representation as we studied before. So if the function f of x, summation of f of x, wj and xj's, is greater than or equal to 0, then we assign h of x as 1. Otherwise, it is 0. So all of those values which give us one, that means their f of x is greater than or equal to 0. Otherwise, it is 0. Assigned h of x is assigned a value of 0. But here we can see it is very hard decision. Okay, if this level is 1 for a value, this point either we are here or either we are here. This classifier is doing this. Either you are 0 for all other things, all other criteria. But if your f of x is greater than or equal to 0, this value, summation of your multiplication of xi's and wi's, then you are given a 1. And at this point, there is a jump. We can see from directly from 0 to 1, a hard jump, hard classifier. We can call, therefore, we call this a hard classifier. But we say we want to make it a little softer. And I will tell you the reason in some time why we are doing this. So we can say h of x can be interpreted as the degree of being read. We are doing this because this hard boundary for 0 and 1, either you are here or either you are there. Either you are healthy, either you are unhealthy. What about a person who is slightly unhealthy? What about a person who is very unhealthy? So if he is slightly unhealthy, how do we define here? There is a clear boundary between yes and no in case of hard classifier. But we want to make it little softer so that our results are better. And there is one more other reason that I will explain to you in a while. So we say that we try to make it a little bit softer. H of x is 1, can be interpreted as a degree of being read if f of x is greater than or equal to 0. And it is 0 if f of x is less than 0. Here we see for all other function values, we say that f of x, your h of x will take the value 0 if it is not greater than or equal to 0. But here we are saying that we have two conditions. If f of x is greater than or equal to 0, then we say that h of x is 1. But if it is less than 0, then we say it is blue. So there is a difference. Okay, so now we can write it as x goes upward from f of x, x is more likely to be read. The more we are away from this boundary, more likely it is read. And as x goes downwards from f of x is more likely to be 0. So if you are here somewhere, if you are touching the boundary, nearly at the boundary or near the boundary, then we decide based on our h of x function, which is defined as 1 plus exponent e of minus f of x. So this is our probabilistic classifier. Rather than a hard classifier, now we have defined a probabilistic classifier, which says if you go above, the more you are away from this line, the more likely it is to be read. And the more you are going downwards from this line, the more likely it is 0. So this is a new classifier now. Softer version of the linear classifier. So this was a hard classifier, either 1 or either 0. And in case of a softer classifier, we say a probabilistic 1 plus exponent minus f of x. If h of x is close to 1, x is more likely read. If close to 0, x is more likely belonging to class blue. Here is the difference. Red is 1, blue is 0. So there are only two possibilities. But in case of red and blue, we can take the value 0.1, 0.2, 0.3, 0.4. As soon as we go, as we are closer to 0, we can take up different values, 0.6, 0.8. So if this is our 0, the values that are closer to 0, they can be defined as blue, and those which are above your 0, the farther you are away from 0, more chances are that it is red. So this is a softer version of your classifier. 0 and 1, blue, red. So this is how we define, and this is a softer boundary. You don't have a clean break here like this. It is a softer boundary. So logistic regression, it has a curve like this. And it is preferred because it has a solution. And the problem with hard classifier is that your h of x, f of x could become non-differentiable. So here is an example. So why hard classifier is not recommended? Because at some point there is no answer to the derivative, because we are taking the partial to find our values. So we cannot, if we cannot define the partial at a point in the function, we say that the solution does not exist at that point. So here is an example. Another example. This is some function. -1, -2, -8, -9. Then we have on the y-axis like this. Then we go positive values of y. Okay, for example, our function takes the value of 9 at this point, and then for 1 point of decrease, it is at 7, and then another point decrease, it decreases a value of 2 again at 5, and then again for 1 unit decrease in x, it has a 2 unit decrease in y, again 2 unit decrease. Okay, so for every 1 unit decrease in your x, change in value of x, one unit change in value of x, there is a 2 unit decrease in the value of y. And what do we call this? Slope. Slope is decreasing, 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 and it is decreasing at a constant rate. So if we define the slope, every time it is decreasing by value of 2. But this value, for example, plotted value, increases like this. Okay, so up to here we can find the slope. It is decreasing, decreasing, decreasing. What about at this point? What is the value of the slope? So here if we calculate from point 2 to point 1, there is nearly 3.5 value of increment. Here we are decreasing and then suddenly our value start to rise here. So if we point, and then it is not going to a straight line, it is slightly curved line. So what is the slope? It is the tangent, and its value is decreasing up to this point. So how can we plot this or present the value of our slope from point -2 to -1? There is a drastic change. Before our value was decreasing before -2. Now suddenly a sharp increase. Suddenly there is a sharp increase. So if we plot, for example, the slope, it will be here something like this, and then the tangent line becomes want to draw so that it is clear. So here, for example, it cuts here and then goes. So suddenly it rises from this -2 point. At -2 it goes to nearly -3, and then cuts it at -1. From -2 to -1 there is a nearly 3.5 increase in the slope. So we can say that our slope starts from here and then it decreases until this point, until here, and then we can see there is no change. There is no change, so slope becomes 0. So I will now plot our slope a little bit thicker so we can understand. So our slope was constantly decreasing with value of -2. Then it suddenly increased from here to here, and then it started to decrease when we have very small tangent lines for the curved, and then at this point it becomes 0. Can you see that there are at this point, let's draw it here, this point and at these points, what is the value of the slope? There is no value. It does not exist. There is a break in the graphs for the slope. So now we call this that your graph or your x value is not differentiable or undefined. Differentiable, undefined, it cannot be defined at the value of -2, from -2, and at the value of +5. There is no link between these 2 points, and there is no link between this point and this point. So what I have shown in this graph, that your slope is basically how it is defined: change in value of y for 1 unit change in value of x. So in this case, for every 1 unit decrease in value of y, x, we had initially there was a decrease of 2. So every time the value decreased by 2, but at the point -2, suddenly the graph increased and the slope was increased by 3.5 points with 1 unit value from -2 to -1. And we find that there is no continuation between the point -2, -3 over here, and then 3 over here, where the points are present. So we cannot find a solution for our graph, for our x at certain values, and therefore we say that the solution does not exist and that function is not differentiable. So the hard classifier, where we have only options of 1 and 0, so it is not suitable to be solved mathematically, because there comes a point where the function f of x is not differentiable and cannot be solved mathematically. So we choose the soft classifier because there is no hard jump at value between 0 and 1. So our function can still find a tangent and we can have a mathematical solution. So we find f of x of the best discrimination given your data, and each data point, data up to sample n from 1 to n, and you have each data point is represented by xi, yi, where xi can have values up to d, and for logistic regression yi can only take the value of 0 and 1, 0 or 1, right? And then we define a soft classifier where we say if the value is, the more the value is closer to 1, we say it is red, and if the more it is closer to 0, we say more it is below the line, we say it is classified as blue or 0, classified as red or 1 here. The more farther you are away from this line, higher the chances and more likely that the function takes the value of 1 or red. And the farther you are downward from this line, the more likely the value is blue. So now we convert it from hard classifier to soft classifier. Then how can we solve this problem, which is where the function classifier h of x is defined as 1 divided by 1 plus exponent minus f of x. This is our classifier function for logistic regression, and this is the value of our function f of x, which is used in the classifier.